we wanted to graph something like f of x equal to, square root's never my favorite, but it's fine. The square root of, I don't know, -4 minus x, how we would graph something like that, right? We could, in fact, let's go ahead and do that. But yeah, I feel like my other students, I really just don't love being so zoomed in. Can I not be zoomed in? Am I just zoomed in forever now? You have to hit this button like 4 times to zoom in or out. I don't know why. It's weird. Is that relatively visible? Enough, maybe. If not, let me know. I'll do something about it. So if I was graphing this, I would probably first maybe rewrite it as the square root of -x minus 4. And I'm thinking of the parent graph as y equal to the square root of x. Right? It's a square root function. I've done some things to it. And whenever I'm dealing specifically with a horizontal shift and a horizontal reflection, which this has both of. And the way I know they're horizontal things is because they're happening inside the function, right? If stuff happens inside the function, it does it horizontally. If stuff happens outside the function, it's going to affect it vertically, which we'll do one of next, just to kind of see the difference. I'm going to look at the horizontal shift first. So y equal to the square root of x minus 4 is going to shift us 4 to the right. So here's my square root of x graph. I'm not drawing this very nicely. That's okay. Here's my square root of, oops, this pen's about to die. For a new pen. Yeah, I really like that pen. It was good to me. Treated me well. Here's the square root of x minus 4. And then the negative on x, my class. Okay. What class are you looking for? Sorry about that. Okay. Well, you're always welcome here. Okay. So, what was I doing? Oh yeah, I was about to do y equal to the square root of -x minus 4 is going to take this graph and reflect it across the y-axis. So it's going to give us this kind of shape. But I will say, if you're faced with a horizontal shift and a horizontal reflection, the easiest way to make sure you get it right is to do the shift first and the reflection second. Really, to be perfectly frank, when it's a square root function like this, the real easiest way to make sure you get it right is to think about the domain. So if I thought about the domain here for just a moment, okay, well, I want the insides to be greater than or equal to 0. If I try and solve for x, I'm going to make it easy, just add x to both sides. -4 is greater than or equal to x, or preferably x is less than or equal to -4. Well, that shows me, oh yeah, I'm starting here at -4, 0, and I have to be to the left of that because x has to be less than or equal to -4. So when you have functions that have domain restrictions like this, it's really useful to think about them because it can help you identify what the shifts and the, the shifts and the reflections should look like. On the other hand, there's too many things. If we had something like g of x equal to 3 times the square root of x plus 1, that's going to affect this graph in vertical ways. The multiplying by 3 is going to stretch it by a factor of 3 vertically. So if I start, and this is always the stretching and the shifting, or sorry, the stretching and the compressing are the things that I always find more challenging to make look accurate graphically. So this is where I have to be a little more precise with my graphing. When I graph the square root function, I typically like to plot the points 0, 0, 1, 1, and 4, 2. And then when I multiply that by 3, same part here. all the y values are going to increase by 3. Sorry, not increase by 3, are going to multiply by 3. So instead of getting the point 1, 1, I'm getting the point 1, 3. Instead of getting the point 4, 2, I'm getting the point 4, 6. It might be off the charts. So there's y equal to 3 times the square root of x. All of the x values have multiplied by a factor of 3. It's kind of stretched out away from the x-axis. And if you had negative values, they would get stretched out negatively away from the x-axis. And then finally, if I was going to finish graphing this, I'd shift them all up by 1. So instead of being 0, 0, I'd get 0, 1. Instead of being 1, 3, I'd get 1, 4. And that's all I really want to graph. But I guess I could do the next one. Instead of being 4, 6, I get 4, 7. 6, 7, 8. 7. So there's what my u for a graph will look like. Here's y equal to 3 root x plus 1. So really what I want to drive home is the whole, if it happens on the inside of the function, it's affecting it horizontally. If it happens on the outside of the function, it's affecting it vertically. That's the kind of key thing I would use here. All right, did that last time. Why am I notes so much? Oh, I know that. Sorry, everything is super funky over here. Yeah. So I want to talk about limits, but I want to talk a little bit more about domain range first. Again, I'll just say, if there are things you want to see, let me know. Yeah.
Question. I understand that you do the addition when it's both a reflection and a shift horizontally. You do the shift first.
Yes.
But I was just wondering, like, conceptually, what is the explanation for why we can't do the reflection first?
You can. So let's say we had something like, in fact, we can even look at the same one again. So let's say we're looking at this, what is it, square root of negative x minus 4. Awesome. Thank you. So let's say that so you're saying instead of doing the shift first, we're going to do the reflection first. Okay. Like, does this ever actually work for me? So really the explanation for why I do it the way I do it is because it always works when I do it that way. And whenever I do it the other way, I usually kind of mess it up. But let's take a look. So I'm going to do the reflection first. So I'm going to shift it. I'm going to reflect it that way. So there's my square root of negative x. And then I want to do the shift. Now I know what it's supposed to end up looking like. I know it's supposed to end up looking like that. So I should end up shifting it 4 to the left. Okay. So yeah, it all, like, my brain just doesn't want to see how to get there. So I want y equal to the square root of negative. I guess we could think of it this way. It's negative x plus 4. You're doing that shift to the left, right? Because it's an x plus 4. X has to be 4 less than it was. But again, right, this works, but it's just harder to think of. So this is correct, but I have trouble getting there. Honestly, the way I often actually think about it, which is also tricky, is I actually kind of look at this and I see, oh, negative 4. I really don't. What I really do is what I did first, actually. What you could also do is you could do it like this and say it's going to be a shift 4 to the left. This is where it gets wonky. And then it's a reflection across this line. But I find that to be tricky, right? It doesn't really, the first way we did it is the most concise way. It's always going to work. It's never going to get screwed up by making some dumb errors. So that's why I do it this way, because it always ends up working for me. Whereas the other way is I'm like, wait, I have to think about the thing and the other thing. And, oh yeah, that other thing. So that's kind of
How would the line flip if the negative outside of the root?
excellent question. In fact, so let me ask you all, since the negative is on the outside, what would we expect to happen? A vertical flip. So things on the outside affect it vertically. So if you were graphing something like y equal to the negative square root of 2x plus 6, we would expect, so usually you want to work from the inside out. So how much are we going to shift to the left? I will warn you, it's a trick question. So it's a trick question. 3, exactly. Because it's really negative square root of 2 times x plus 3. So you can either shift it left 6. Right, that's your first step. Here's y equals the square root of x plus 6. But then this multiplying by 2 is going to give you a horizontal compression by a factor of 2. What I like to think about when I'm thinking about this, like why is this compressing it by a factor of 2? Well, here's the idea. Here are my x and y values here. If x is negative 6, y is 0. If x is negative 5, y is the square root of 1. If x is negative 2, y is the square root of 4. If x is 3, y is the square root of 9. If x is, looks like one more value, 10, y is the square root of 16. But now, the x values, well, since they're getting multiplied by 2, I want to produce the same y values, the x values have to be half as big as they were. Right? Now, instead of having x equal to 6, I really want 2x to equal, sorry, I said 6, I meant negative 6. I want 2x to equal negative 6, so that the y value is the square root of negative 6 plus 6. And I want 2x to equal negative 5, so that the y value is the square root of 1. And I want 2x to equal negative 2, so that the y value is the square root of 4, which is 2. And so on. I want the same values in these columns, but that means the actual x values have to be half as big as they were. So my graph squashed in, I think squashed, compressed in by a factor of 2. My x values are now there. And I know I didn't graph this very precisely before, so I'm kind of like, yeah, I should have graphed this one more precisely, but that's kind of the point. Is it's going to look more like this. If x is negative 1, you get a y value of 2, sure. If x is 5, you get a y value of 4. So that's kind of the idea, right? Or you could instead just factor out the 2 first, do the shift to the left by 3, and then kind of see it there. And then to finish it off, the negative out front is going to flip it over vertically. So I'm gonna leave myself a whole lot of room here. That's terrible, James. Let's just use another piece of it. So it'll look like that. And again, I know this graph is not super precise, right? Like I could plot more points. I know that x is negative 1, and negative 2, and so on. So you can also, so I think actually this is a great time to utilize Desmos because it really can help you see as you add in each little piece what's going on. So for example, we can start with the square root of x. Oops, or z. No, let's do x. And then you can either do the shift first and then see that when you multiply by 2, check it out. It shrinks by a factor of 2. You can also graph each one if you really wanted, right? You can say like, there's the square root of x. Oops, maybe some square rooting there. I don't need that slash either. And then you can see the next one. And you can either do, right, this, and then this. And then put a negative in front of it. Let's just be smart and copy this. I just flips it right over. But there's other ways we could have gone, right? If you wanted to, you maybe could have done, right? So you could also go this way first and say, you could do the 2x as your first kind of transformation. Let me unclick some of these so we can kind of see, right? The 2x just compresses it horizontally, right? It's smushing that red graph in towards the y-axis. And then if we add the 6 on there, it's going to shift it 3 to the left, because really what you're doing is you're not adding on 6, you're adding on 3 to the x before you. So as you kind of think about the order of operations here, right? If you have 2x plus 6, you're really doing x plus 3 first and then multiplying by 2. So we usually kind of think about a shift before a squash or a stretch. Yeah. Transformations. Super fun. Let's look at a little more domain stuff, and then we will move on and start talking about some limit stuff, I think. So let's look at, oh, here's a good function. Look at f of x equal to, let's see, sorry, where you go? All right, brain, yeah, x times sine of x. The function, oh yeah, question. Oh yeah, you might want to see what I'm writing. Thank you. Really, if you can't see what I'm writing, just feel free to don't even wait for me to call. Just be like, James, we can't see what you're writing. Totally fine. I'm not offended at all. Is there any way of finding the domain and range of a function without graphing first? Definitely some of the time. And we'll look at an example or two in just a minute. This one, we might be able to, in fact. So let's see, what do I want to say about this function? Let's talk about first, is it even or odd? Well, it's good to remember that sine is an odd function. So if I want to see if it's even or odd, f of negative x is going to equal negative x times sine of negative x. Now, here's a key thing. Sine of x is odd, which means sine of negative x equals negative sine of x. It's a key thing to remember. We talked about it last class. I know it was a whole like 5 days ago, but we did talk about it. So this is going to equal negative x times negative sine of x. And the negative times a negative is a positive. So it's going to be positive x times sine of x, which is the original function, which means that it's an even function because f of negative x is equal to f of x. And it's kind of worth noting that if you take two odd functions and multiply them together, you do get an even function. Some more typical examples of this, the ones to keep in mind, are like x squared and x cubed. Or really any even or odd power of x, right? X to the fourth is an even function. X to the sixth is an even function. And if you multiply two even functions together, you get an even function. Right? X squared times x to the fourth is x to the sixth, which is an even function. If you multiply two odd functions together, you also get an even function. x cubed times x to the fifth is x to the eighth, which is a given function. I know these are not proofs of the things being true, but they're good examples of how they are true. Whereas if you multiply an even function times an odd function, x squared times x cubed is x to the fifth, which is also an odd function. So kind of neat to know. Let's talk about so this one is even, which means it has symmetry about the y-axis, and we can kind of graph it. The thing I would note about this is I know when sine is equal to 0. I know that sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0, sine of any multiple of pi is 0. When we start graphing this, pi, 2 pi, 3 pi. I know sine is positive from 0 to pi, so it's going to do something kind of funky like that, and then it's going to hit 0. And then between pi and 2 pi, sine is negative. So it'll do something kind of like this. And between 2 pi and 3 pi, sine is positive. And it's going to kind of keep doing this weirdness, where it's oscillating back and forth. In fact, it does the same thing to the left. And here my graph is probably going to start to look terrible because it should be symmetrical. But drawing something symmetrical when you've already drawn one side of it can be a little challenging. So just pretend like this left side looks the same as the right side. That's all right. That's pretty good. Has some big symmetry to it. And this graph has an infinite number of x-intercepts. We would say that the x-intercepts are k pi comma 0, where k is an integer. Or someone might do this. You could also just list them out, right? Like 0 pi, 2 pi, dot, 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 dot. That would be also fine. There was something else I wanted to mention here, which is what's the range of this? I mean, it kind of looks like it's just going to get bigger and bigger and bigger, but we don't actually really know. Here's how we can kind of take a look at it. And this is actually a very common thing we do a lot for things with sine or cosine. Really, really useful through your whole calculus career to remember that sine of x is always between 1 and -1. That one piece of information is going to serve you well. Take it to heart. It's also true for cosine. But then you can multiply everything by x so that -1 times x is less than or equal to x times sine of x is less than or equal to x. And specifically, that's our function. Our function is between -x and x. Well, okay, I know how to graph that. Here's y equal to x. Here's y equal to -x. And I can do the graphic. I'm going to try and do the graphic again. It's going to look maybe so-so. Now, here's a piece of information I'm using to draw this graph. I know that when x is pi over 2, sine of pi over 2 is equal to 1. Right? The top of the unit circle, sine is 1. The bottom of the unit circle, sine is -1. So specifically at those values, like when x is pi over 2, x times sine of x is also going to be pi over 2. What I'm really trying to say is when x is pi over 2, this and this are actually equal. So at pi over 2, it actually hits that part of the graph right there. And at 3 pi over 2, it's actually going to touch right there. And at 5 pi over 2, it's actually going to touch up here. So the graph kind of looks like this. And it keeps doing this sort of thing. And every odd multiple of pi over 2, it's going to actually go back and hit one of the either y equals x's or y equal -x's. And the same thing to the left here, which is not going to look very good, but oh yeah, that's okay. Yeah, I promise delivered. It doesn't look very good. But we can kind of see from this, oh, the range is everything, right? This is going to continue just getting bigger and bigger and more negatively big as well. So our range here, and again, I will agree, we did kind of have to graph this one, but our range is going to be everything from negative infinity to infinity. Our domain also, right, there are no domain restrictions here. Everything from negative to infinity. Yeah. But let's go ahead and kind of look at a different question where we might not be able to graph it, or graphing it might be, it's not that we couldn't graph a lot of things, it's just we might not want to. So let's look at something like this. F of x equal to the square root of x squared plus 2x minus 8. And I want to find the domain and range. Okay, well, I think we talked. So I will admit fully, I always have trouble remembering what I've done in each class because so many, like I'm also doing the Co-21A class, and a lot of the material in the beginning really overlaps. So I might have talked about the domain things in this class last Thursday. I might not have. I feel like I did, but maybe I didn't. So just as a real quick kind of thing here, here are the usual domain issues. If your function has division by some stuff, we don't want that stuff to equal 0. So we usually start by saying, I'm going to exclude where the denominator is equal to 0. Or if our function is equal to the square root of some stuff, we're going to start by setting the stuff to be greater than or equal to 0, because we can't take the square root of a negative number. And lastly, if our function is a logarithm of some stuff, doesn't matter what the base is, the base should be a normal number, meaning when you take a logarithm, the base should either be a positive integer or the number e. Those are the only, like you could have a base of 1/2 or 2/3 or square root of 2. No one is ever going to ask you to talk about a logarithm whose base is the square root of 2 or 1/2 or 2. It's just weird. It's not incorrect. It's just abnormal for logarithms. So like log base b of some stuff, we want to start by setting that stuff to be strictly greater than 0. And these are the 3 domain things you should remember. If you're asking yourself, what's the domain of a function? These are the things we have to consider. Is there division by 0? Is there a square root of a negative? Is there a log of a 0? If none of those things are showing up, your domain is everything. I will step aside for just one thing. It's not entirely true. There is one other small class of functions that also have domain issues. They're inverse trig functions. We will eventually talk about them. But for the most part, when you're talking about domain, these are the 3 big things. Division by 0, square root of a negative, log of a 0 or negative. Yes, maybe. I pressed the button like 4 times. The problem with zooming in is it's too zoomed in. Like I want like an in-between zoom level. If I made this bigger, would it help? Oh, I know it. Let me try a thing. That doesn't help, but there was a thing I did before, resolution, custom. Let's try that. Sorry, 1 second. So I'll make this window like taller. Can I make it taller? No, you're lame. Sorry, I can make it wider. Doesn't want to be taller. Well, that's something, I guess. Does that help? Okay. So back to the question we were looking at. We want to find the domain range of this. So we're going to set the insides to be greater than or equal to 0. And typically, we usually solve an inequality like this by factoring. So I can factor this. It factors as x plus 4 times x minus 2. And then we find where that expression is equal to 0, which is x equal to negative 4 and x equal to positive 2. We plot those on the number line. in the appropriate places, right? Make sure the -4 is to the left and the +2 is to the right. And don't put a 0 on there unless you actually, and meaning don't put a 0 on there unless it's actually one of the numbers that makes the expression equal to 0. And then we're going to determine where this thing is greater than or equal to 0. So pick a number larger than 2, like 3. 3 + 4 is positive, 3 - 2 is positive, the whole thing's positive. Pick a number between -4 and 2, like 0. And 0 + 4 is positive, 0 - 2 is negative. Pick a number over here like -5. Or you can do the whole thing where there's another way of doing this. If you're trying to solve an inequality where you say, oh, these factors have odd powers. The powers are 1. And when the power is odd, whenever you go from one side of an intercept or 0 that comes from a factor with an odd power, the sign of the expression is going to change. So when you go from this side of 2 to this side of 2, since 2 came from a factor that has an odd power, the sign changes. On the other hand, if it has an even power, the sign is the same. And the whole reason is because when I go from over here, a number larger than 2, -2 is positive. Whereas a number in here, a number less than 2, -2 is going to be negative. So this factor is changing signs. And since it's to an odd power, we see that sign change. Or if it was to an even power, it wouldn't matter, because a positive thing squared or a negative thing squared is still positive. And then over here, the sign would also change. Because in here, whatever you have +4 is positive, but over here, whatever you have +4 is negative. And then you have a negative times a negative, which is positive. So our domain here, everything from -infinity to -4, including -4, because we want to take the square root of 0. Square root of 0 is 0, it's totally fine. And -4 makes the expression equal to 0. Union, everything from 2 to infinity. And something else I want to say about that, maybe not. As far as the range goes, the range is always where you have to kind of just like talk it out sometimes. So there is a very specific method of finding the range of a function if you can find the inverse function. Not really an option here. Finding the inverse of the square root of x + 2x - 8, probably not impossible. It's probably more trouble than it's worth for sure. Here's how I really talk about the range. If x is equal to either one of these endpoints, the y value is going to be 0. If I look back at my function, f of x equal to the square root of x squared plus 2x minus 8, I can see that f of 2 is equal to 0. I plug in 2, I get 4 plus 4 minus 8, that's 0, square root of 0 is 0. And that's the lowest the range values can be, or the y values can be, because whenever you take a square root of something, you always get out non-negative numbers. So now the only other question you have to answer is, how large can this get? Is there a limit to how big this can be? Sometimes the answer is yes. I meant for the answer to be yes, but I accidentally wrote the problem in a different way than I meant to. Sometimes the answer is no. And here the answer is no, because if we think about it, so if we look just in this domain here, if you let x get larger and larger and larger, like say x was 1,000, and you're gonna have the square root of 1,000 squared plus 2 times 1,000 minus 8, which is pretty close to just the square root of 1,000 squared. Right? The smaller things don't count as much as x gets bigger. So if x is 1,000, you're gonna have something that's pretty close to 1,000. I mean, I don't know exactly. We can figure it out. It might actually, I think it is worth our while for just a second. So here's an easy way. Oh, come on, let's just close all these things. So if I was looking at, not that we need to graph it to actually see the range, I'm graphing it more just to calculate a value. So look, it looks like it's just getting bigger and bigger and bigger. But if we actually want to calculate a value, we can start a table. So if I plug in x equal to 1,000, oh yeah, the y value is really close to 1,000. Really what's happening here is essentially y equals x is kind of like a slant asymptote, meaning as the x values get larger and larger and larger, the y values and the x values get closer and closer to each other. Right, if you go with x equal to 1,000,000, wow, okay, don't be ridiculous. There, let's do 100,000, right? The y value is very close to 100,000. So what I'm trying to point out is, as things get very large, the non-dominant terms, the 2x and the -8, are essentially negligible. They don't really matter if x is very large. But this kind of helps to see, oh yeah, if x gets big, the y values also get big. And the x values can get big forever and ever, so the y values can also get big forever and ever. So the domain, sorry, the range here is everything from 0. Oh, yep, of course. We should do one more. That's a good one. We'll do a couple more of these domain range questions, take a bathroom break, then we will actually start talking about some more stuff. Yeah. I like having a document camera, but sometimes I like hit it accidentally and it's not good. You shouldn't hit your document camera. You should treat it nicely. Let's look at this function. F of x equal to let's do this one. Sure. The square root of x to the 4th times x minus 3 to the 7th plus x to the 5th times x minus 3 to the 6th. And you might think, I don't know, you might not. You might think, though, that this looks somewhat contrived, but I will say this format comes up actually quite a lot when you take the derivative of something using a product rule. So finding the domain of an expression like this is actually not an out there question. So we want to set the insides equal to, sorry, not equal to, greater than or equal to 0. And now here's the thing. When you're solving an inequality like this, you really want to factor it so that it's a bunch of stuff multiplied together. And very specifically, addition is terrible. And I hate the way this expression is written right now because it's not helpful. Right? I don't have a bunch of things multiplied together, which I want. Because when a bunch of things are multiplied together, it's really, really, really easy to see if the whole expression is positive or if the whole expression is negative. Whereas if they're added together, well, I don't know, if I take x equal to 1, I just have to think about the numbers. Right? Because this here is -2 to the 7th. Okay, 1's probably pretty easy. This is -2 to the 7th, and this is -2 to the 6th. It's going to be negative because -2 to the 7th is more negative than -2 to the 6th. Right? But I'm doing too much thinking already. Right? I shouldn't have to think about which of those is bigger. The point is, we want to factor. So what can I factor out from both of these pieces?
X minus 3.
Yes. How much x minus 3?
That's the power of 6.
Yeah, you can say 6 of them, or you can say x minus 3 to the 6. I know 6 of them seems kind of weird because like it's a power, not a coefficient, but we know what we're saying. That is one thing I can factor out. What else can I factor out? Thank you. So then when I do that, from this first piece, what's left? An x minus 3. And none of the x to the 4th, right? Because I factored out all the x's. From this second piece, what's left over? An x. And now I'm pretty stoked because I have an x to the 4th. And I'm writing this in the opposite order. X to the 4th times x minus 3 to the 6 times an x minus 3 plus x, which is a 2x minus 3. And now I've got this very nicely factored. And I can find all the zeros or solutions, if you will. X equals 0, 3, and 3/2 are the values that make this expression 0. So those are the numbers that are going on my number line. If I've got 3 numbers, I've got 4 separate intervals to check. Right? There's always one more interval than the number of zeros you have. All right, well, let's see. So start to the right. Pick any number bigger than 3. You can pick 4. You can pick 40. You can pick 4 billion. Doesn't matter because if your number is larger than 3, that's positive. A number bigger than 3 minus 3 is positive. A number bigger than 3 times 2 minus 3 is also positive. But you should, right? It's easier if you just pick a number, right? Pick 4. Yeah, 4 to the 4th is positive. 4 minus 3 is positive. 2 times 4 minus 3 is also positive. That's why you pick a number instead of speaking super generally. A positive times a positive times a positive is positive. Okay. Now, if we pick a number between 3/2 and 3, the best choice here is 2, right? There are other choices, but 2 is the obviously best choice because it's the easiest to pick. 2 to the 4th is positive. 2 minus 3 is negative, but a negative number to an even power is still positive. And 2 times 2 minus 3 is positive. So it's a positive times a positive times a positive still, so it stays positive. And that's what I was trying to say before about if the point you're crossing over comes from a factor that's raised to an even power, so an odd power, the sign of your expression is going to stay the same. And even though the insides there are changing from positive to negative, that even power is kind of not letting us see that change. On the other hand, when I cross from this side to this side, I'm crossing 3/2, which came from this factor, which is raised to an odd power. So we should see a sign change here. We will. We pick x equal to 1. 1 to the 4th is positive. 1 minus 3 to the 6th is also positive. It's a negative to an even power. But 2 times 1 minus 3 is negative, and it's raised to an odd power, which is still going to make it be negative. And a positive times a positive times a negative. And then when we go over to the other side of 0, like pick -1, -1 to the 4th is positive. -1 minus 3 to the 6th is positive. And 2 times -1 minus 3 is negative. And a positive times a positive times a negative is negative. And once again, we're seeing the same sort of result. When you cross over a thing that came from a factor that has an even power, the sign stays the same. So what's our domain here? Well, I want where it's non-negative. I want where it's positive, positive, or 0, or 0, or 0. Well, this one's going to be fun to write. So the domain here, what's the leftmost? Oh, sorry. What's the leftmost thing that's in our domain? 0 is the leftmost thing, right? 0 is definitely in our domain. X is allowed to be 0. But it's the only thing that's like, right, it's by itself. It's all alone. And the way we write that is with braces. If you want to write a thing that's containing just one single point, this notation is the set containing the element 0. People, I don't want to encourage you to do this because people might not be okay with this. People are usually okay if you write something like this, but I would really strongly warn you against it because I could definitely see some of your professors being like, nope, that's terrible. Don't write that. So definitely you don't really want to write this. You want to write that. And then we have this, everything from here onwards, right? There's no breaks after that. So everything from 3/2 to infinity. Infinity always gets the parentheses, right? In case I hadn't said that before. To clarify, did you say that there is one more x-intercepts than what you get? I think what I said, I'm not sure, but I believe what I said is you always have one more interval than the number of x-intercepts. So this one had, or I should say the number of zeros, right? This one had 3 values that made the expression equal to 0, and we have 1, 2, 3, 4 distinct intervals. And that's always going to be the case. Because whenever you add another x-intercept, you're cutting your, right? If you have no x-intercepts, you have one whole interval, like the entire real number line. And then every time you add an x-intercept, you're cutting it into an initial piece. So one intercept gives you 2 pieces, and then another intercept gives you another piece, and so on and so on and so on. So I think that's what you're asking about. If it's not, please let me know. Let's see. Interesting. I was just noting that the person who wrote these notes, not me, missed the 0 on the domain there. It'd be easy to miss. I'll have to let Grant know. Sometimes everyone makes mistakes. I'm not casting any aspersions on Grant. Grant's great, but I should let him know there's a little error there. Yeah. Let's go ahead, and I need to pee, so let's take a quick break. I'm going to pause the Zoom so that when I edit it later, I don't have to deal with this so much. Remind me when I come back to unpause the Zoom so that it keeps recording. So still don't understand how 0 works as the domain. So let's talk about it. So if we look back at the original expression, which I'm going to go to over here, here's my original expression. If we plug in 0, let's see if it works. So f of 0 is going to be, let's see, I'm going to get the square root of 0 to the 4th times 0 minus 3 to the 7th plus 0 to the 5th times 0 minus 3 to the 6th. You can see that. And then that's going to equal, well, let's see, 0 to the 4th is 0. 0 minus 3 to the 7th, I could calculate, except I know that 0 times anything is going to be 0. And the same thing is true here. 0 times anything is going to be 0. And 0 plus 0 is 0. And what's the square root of 0? Good old 0. So that's why 0 works in the domain here, because we can plug in 0 to the function and get a real number as a result. On the other hand, -1 would not, for example, would not be in the domain. If you plugged in -1, you would end up taking the square root of a negative number. It'd be kind of, I mean, we can show the work here. Maybe. So if I look at f of -1, for example, it's going to be the square root of -1 to the 4th times -1 minus 3 to the 7th plus -1 to the 5th times -1 minus 3 to the 6th. And I don't really need to calculate this. Here's what I'm going to do. I'm going to say this is the square root of -1 to the 4th is +1. -1 minus 3 to the 7th is -4 to the 7th. -1 to the 5th is just -1. And -1 minus 3 is -4 to the 6th. And here's what I have. I have a negative number minus a positive number, which makes it even more negative. So this for sure is negative, which means we can't take the square root of a negative. So -1 is not in the domain, which we already knew because we showed it before, but here we are seeing some additional proof of that. So hopefully that clarifies things. All right, let us move over to start talking about some limits. Limits are not extra, they're super important. Over here, so I can scan them later. All right. I think I'm like hiding from you guys while I drink. I'm like, you can't see me, I'm drinking. That's like the fool, but no, sorry. Okay, so let's go ahead and graph a piecewise function. Let's graph. Yeah, thank you. I'm going to zoom back out for a moment here, but let me know if you would like me to zoom back. I'm going to try and write a little bit bigger. Let's graph f of x equal to this piecewise function. X squared plus 1 when x is less than or equal to 0. X plus 1 when x is bigger than 0 and less than 3. And the square root of x plus 1 when x is bigger than or equal to 3. All right. So when I'm graphing a piecewise function, I'm just thinking of all the pieces, kind of what they look like individually. So I know that x squared plus 1 looks like the usual parent graph of the parabola shifted up 1. And x plus 1 looks like the line. I mean, really, it's a line, right? Y equals x plus 1 is just a line that has an x-intercept of -1 and a y-intercept of +1. You could also think of it as the line y equals x shifted up 1 or left 1. But usually with lines, if you're thinking about how to graph a line, you should really just be thinking of where are the intercepts. That's usually the easiest way. And the square root of x plus 1 is looking like the regular square root graph shifted 1 to the left. So if I graph this, well, I want x squared plus 1 when x is less than or equal to 0. So I know that when x is equal to 0, I'm going to get the point 0, 1. And it's just going to look at the left side of that parabola. So I could give myself one more point if I really wanted to. When x is -1, I get -1 squared plus 1, which is 2. So there is x squared plus 1 when x is less than or equal to 0. And then, well, x plus 1 when x is between 0 and 3. So it's going to be important to see what's happening at 3. I know that y equals x plus 1 looks like this line here. That's going to go this way like that. But I only want between 0 and 3. So I only want from, let's see, when if x could be 0, I would get the point 0, 1. If x could be 3, I would get the point x is 3 and y is 4. Now I don't actually get that point because x doesn't actually get to be 3 for this piece of the piecewise function. So it's going to look like that. I have the point 0, 1 and 1, 2 and 2, 3 and almost 3, 4. I have the point like 2.9, 3.9 and 2.99 and 3.99. Right, there's a lot of points that are close to 3, 4, but I don't actually have the point 3, 4. And then the square root of x plus 1 is going to start when x is equal to 3. So when x is 3, I'm going to get y equal to the square root of 3 plus 1, which is 2. I'm going to get the point 3, 2. All right, and not that I'm going to graph all this, but I'm thinking of the square root graph that's doing this. Right? It's doing like that. Right, you guys can kind of see what I'm trying to draw out there without actually drawing it. So it's just going to continue on this way. If you wanted to, you could plot another point. I would plot the point. I would pick the next convenient value of x. So I just took the square root of 4, which is, and got 2. The next convenient value of x is when I get to take the square root of 9. So x needs to be 8. Y is going to be 3. So that's kind of your next value. I probably wouldn't actually do that one because 8's kind of far, but okay. 4, 5, 6, 7, 8. And the y value is 3. So yeah, like that. So here's my piecewise function. And I, oh yeah, go ahead.
He said, wouldn't it be an open circle for 0 for the second one?
Well, so yes and no. So it would have been if we had just graphed like this middle part here. So if I was just graphing y equals x plus 1 from 0 to 3, it would look like this. It would start there with an open circle, and it would end at 3, 4 with another open circle like that. Oops. Sorry. But then the thing that's happening is the x squared plus 1 graph is filling in that open circle because it has the point 0, 1. So that's why it's a closed circle there. So if you have a closed circle overlapping with an open circle, the closed circle, I guess, wins. I mean, it's not that it wins, it's just it's defining something that wasn't defined already. So these happen to match up with their y values. Right? Whereas this, right? So to kind of continue on in that way, if this square root function was shifted up by 2, then this part would fill in the closed circle, the open circle right there. It's not, but if it was, then that's what we would get. I will also point out this function is discontinuous. I know we haven't defined continuity yet, but it's worth having a good visual idea of what something continuous versus discontinuous looks like. And I can see it's discontinuous because there's a break. Or as people like to say, you couldn't draw this graph without lifting your pen off the paper. Whereas a continuous graph, you should be able to draw without lifting your pen or pencil off the paper. That's kind of the very easy way of deciding something is continuous versus not. So not continuous because although I could draw all of this part without lifting my pen off the paper, I got to here and then I had to, jump down to there, lifting my pen off the paper to get there. So this is discontinuous, and we will definitely get a better definition of discontinuity and continuity later on. Well, you have an open circle of 0 as well. Oh, sorry. Yeah, sorry. So let's ask some questions. Let's ask ourselves, what value does y approach as x gets close to 0 from the left side? So here's how I like to look at this graphically. As x is coming at 0 from the left, what are the y values of the function getting closer and closer to? The x values are getting closer to 0. What are the y? So what's the point that we're getting close to there? Right. Well, I would say the whole point is 0, 1. But yes, the y. Oops. See what I was saying? I'm killing this thing here. So the y values are getting closer and closer to the value of 1. Y approaches 1. Another way sometimes people say this, although it's not 100% like mathematically correct, but people think of like a really, really small value, or I should say a value that is really, really close to x approaching. So you can kind of think of like, for example, f of negative 0.00001 is essentially 0 squared plus 1. Because again, when we're plugging this into, well, if x is a little bit negative, we have to pick the piece of the piecewise function where x is negative, which is when x is less than 0. So I'm plugging it into there. A very, very negative, small negative number squared is going to be essentially 0. And that's going to be 1. Yeah. Let me do this to make it a little bit easier to see where I want to be. Or any more mathematical notation. Now, again, for those of you in Molassi's class, you're probably not going to see this yet because it does things in a different way. We're going to say that the limit as x approaches 0 from the left of the function is equal to 1. And literally all this means is what we just said. It doesn't actually, oh, sorry, you can't see that. It doesn't necessarily mean that the function is equal to 1 when x is equal to 0, although it is in this particular example. All it means is that as x gets closer to 0 from the left side of 0, the y values get closer to 1. And what I really want to drive home, I will repeat many, many, many times, is that when you're talking about a limit, you don't actually care at all what happens at the x value. Meaning this limit is not concerned at all with what is happening when x is actually equal to 0. All this limit cares about is what is happening as we approach 0. So I will say that numerous times again. Don't worry. If you heard it once, you'll hear it again. Let's look at the other side. What happens? Sorry. What happens as x approaches 0 from the right? Well, the way we're going to write that, well, in fact, actually, first of all, y is also approaching 1. Right? If we look at our piecewise function, right, when x is a little bit bigger than 0, right, that's the right side. So when someone says the right side of something, they mean the bigger side. The left side of something is the less than side, right? It's just a number line. If you're to the right, you're larger. If you're to the left, you're smaller. We look at the piecewise function when x is a little bit bigger than 0, y is equal to x plus 1. So if x is very, very close to 0, x plus 1 is very, very close to 0 plus 1, which is essentially what we're going to call 1. So the way we'd write this using this notation is the limit as x approaches 0 from the right of our function is, well, again, we said it was essentially 0 plus 1. Which is 1. And again, all this means is that as the x values get closer and closer to 0, the y values get closer and closer to 1. So I should really point out x gets closer to 0, and the y values, or if you prefer, you can say the function values. It's the same idea. Get closer to 1. That's what's happening with that expression there. And that's what the limit is always talking about. What's happening with the y things as the x things do this, as the x things get close to some particular number. And in this case, this table feels like it'd be big enough, but sometimes it doesn't feel like it's big enough. Maybe if you condense all your stuff into less spacious area, it wouldn't not be so small. Sorry. I want to say is in this case, since the limit from the left and the limit from the right have the same value, we can say that the overall limit or the double-sided limit, as people also call it, the limit as x approaches 0 of the function is equal to 1. Because the limit as x approaches 0 from the left of f of x is equal to the 1 value, which is the same as the limit as x approaches 0 from the right. And this is generally true. For a limit to exist, the left-hand limit and the right-hand limit both have to exist and equal the same value. In fact, that's where we're going with the next part here. So we look back at our piecewise function. We're now going to explore. Gosh, I'm happy to be zoomed in for you guys, but it makes things challenging. So we're now going to explore what happens when x approaches 3. And just graphically, we can see that as x approaches 3 from the left, what are the y values getting closer and closer to? Yeah, 4. Sorry, I should have written this out right. 1, 2, 3, 4. Whereas when x approaches 3 from the right, what are the y values getting closer and closer to? 2. Exactly. So let's write that down. So we can say, okay, we can say that the limit as x approaches 3 from the left of f of x. Well, that's the piece that's the x plus 1 piece, right? Because that's when you're less than 3, we're using this piece of the piecewise function. That's going to equal essentially 3 plus 1, which is 4. Versus the limit as x approaches 3 from the right of f of x. Well, for if x is larger than 3, then we're using this piece of the piecewise function. And if x is larger than 3, we're using the piece square root of x plus 1. Can I see your symptom survey, please? And so that's going to be essentially the square root of 3 plus 1, which is 2. Thanks. So, since the left-hand limit and the right-hand limit are not the same, we get the limit as x approaches 3 of f of x does not exist. Right? There is no one value that the function is getting closer to as x comes at 3 from either side. Right? There's a mismatch there, or what's called a jump discontinuity. So, and this is because the limit from the left, limit as x approaches 3 from the left, is not the same as the limit as x approaches 3 from the right. So here's what we get to say. If the limit as x approaches some c value of f of x is equal to L. So this is very general notation, right? We're saying if x is approaching some value and the limit is equal to some value, that's only, I kind of wrote this a little backward. Let me fix it. What we actually really say is if the limit from the left and the limit as x approaches c from the right are equal to the same value, then it is true that the limit as x approaches c from either side is equal to that. And what I should really say is this is an if and only if statement, meaning if this is true, then this is true, and vice versa. If this is true, then this is true. So if someone says the limit exists, you automatically can conclude that the left-hand limit and the right-hand limit both exist and are equal to the same value. If someone says the left-hand limit and the right-hand limit exist, you can automatically conclude that the actual entire limit exists and is equal to the same value. So that's an if and only if statement, right? If the first thing's true, then the second thing's true, and vice versa. The second thing's true, then the first thing's true. Let's see here. So let's look at some other piecewise functions. Make sure I'm in screen. So let's look at f of x equal to x cubed plus 2x when x is less than 1, the cube root of x plus 5 when 1 is less than or equal to x is less than or equal to 8, and x minus 1 when x is bigger than 8. And although we could graph this, I really don't want to. It's a little bit messy, and we don't need to be able to know what's happening with the limits. So I want to ask about 3 different limits here. I want to know what's the limit as x approaches 1. What's the limit as x approaches 8 of f of x? And what's the limit as x approaches 10 of f of x? Oh, sorry, I guess we kind of want to see the function though as we do this. So for x approaches 1, we're going to look at the left and the right hand limit because we can see that there are 2 different functions on either side of 1. Right? There's a function, or I should say, there's a piece that this function is defined to be on the left of 1. There's a piece that this function is defined to be on the right of 1. So for this one here, I'm going to do the limit as x approaches 1 from the left. And I'm going to fill in what piece of the function I get. So when x is less than 1, right, when x is left of 1, I like that left and less, those are the same letter. When x is less than 1, what piece is our function actually equal to? The top, the middle, or the bottom piece? Exactly. So I'm just going to take the limit as x approaches 1 from the left of f of x and write it as a limit as x approaches 1 from the left of x cubed plus 2x. And here's the nice thing about limits. Well, one of the nice things. A lot of the times, if you want to say what the y value is getting closer to, you can just substitute this value in. Right? If you graph this, I will graph it in a second, you're not on this paper. Right, but if I just plug in 1, I'm going to get 1 cubed plus 2 times 1, which is 3. And let's go ahead and look at the graph here. Don't worry, I'll show this back in just a second. If we look at y equal to x cubed plus 2 times x, and right, we start picking, I mean, you can literally see that when you plug in 1, you get a y value of 3, right there. But that's not actually the point. The point is that as the y values get closer and closer and closer to 1 from the left, sorry, as the x values get closer and closer to 1 from the left, the y values get closer and closer and closer and closer to 3. It doesn't actually matter that it's equal to 3 there, but it is equal to 3 there. So what I'm trying to say in a lot of words is that you can just substitute in the value of 1. Similarly, if I want to find the limit as x approaches 1 from the right, I'm going to pick the piece of the function when x is bigger than 1. Now, you might say, well, James, there's 2 pieces there. There's this piece here, x is definitely bigger than 1. And there's this piece here where x is definitely bigger than 1. But we want x to be getting closer and closer to 1, meaning x should be like 3, and then 2, and then 1.5, and then 1.1, and then 1. Right? It should be x definitely just bigger than or equal to 1. So we should be using this middle piece here for the limit as x approaches 1 from the right. So when we do that, it's going to be the limit as x approaches 1 from the right of the cube root of x plus 5, which is going to be the cube root of 1 plus 5, which is 6. And those are not the same. So that means that the limit as x approaches 1 of the function does not exist. And we typically abbreviate that with a dn. Because the left-hand limit and the right-hand limit are not the same. Let's look at what happens when we approach 8. Sorry, no, it's like I'm playing like a puzzle here. So let's approach 8 from both sides. Limit as x approaches 8 from the left. Well, we're using that same piece actually. We're going to be using this piece right here because that's when x is less than 8, but still close to 8. So we're taking the limit as x approaches 8 of the cube root of x plus 5, which is just going to be the cube root of 8 plus 5, which is 2 plus 5, which is 7. We approach 8 from the right. So limit as x approaches 8 from the right. Now we're using the piece of the function where x is larger than 8, which is this piece here. And we're getting 8 minus 1, which is 7. And those are the same. So that means that the limit as x approaches 8 of the function is equal to 7. If the left and right element are the same, limit exists and it's equal to the same value. All this means is that as you approach if you approach 8 from either side, the function happens to be close to the same value.
Is the function piece on x minus 1 when x is greater than 8?
That's correct, yes.
Okay, so shouldn't we use a value of x that's greater than 8?
That's an excellent question. So yeah, I love this question. So how do I approach it the right way? Here's the thing. You're right. X actually doesn't get to be 8. But what the problem here is, what does this notation actually mean? Well, it's asking you, as x gets super extra duper close to 8, what is the y value getting closer and closer to? So let's pick a value of x that's larger than 8. We can pick 9. Let's make a little table over here. So if x is 9, the y value is going to be 8. But x can be closer to 8 than 9, right? We can pick something closer for sure, like what? Like maybe 8.5. Then y is going to be 7.5. Can I get closer to 8? What's the number that's closer? Sure. What's my y going to be? Okay, can I get closer? Can I get closer? Can I ever stop asking the question, can I get closer? No. Right? No matter how close we get, you can always get closer. Right? And that's actually something that is a true fact about the real numbers. They're what's called dense, meaning no matter how close two numbers are, you can always find a number in between them. So since the real numbers are dense, the x values can get as close to 8 as you want. And so the question we're asking is, as the x values get closer and closer and closer and closer forever to this number 8, what number do the y values appear to be getting very, very, very close to? They're not actually equal to them, but what are they getting close to? 7. But right, it's very tempting to be like, well, we need to be quote unquote bigger than 8. So we pick like the next biggest integer. That's a mistake, right? We want to be like, I'm going to get super extra close and then cut off the decimal. What happens in real practice is you literally just substitute it, even though x is technically bigger. Because, let's go to the graph here. Yeah. So let's actually graph this piecewise function. And then we had the cube root, which I'll write as x to the 1/3 plus 5. And that's when x was bigger than or equal to 1, less than or equal to 8. And then what's your problem there? Oh, I see the problem is okay, fine. Okay. Dramatic, Desmos. There we go. Sorry, I'm hitting the wrong buttons is the problem. There we go. And then finally, the last piece of the function was x minus 1 when x is bigger than 8. So here's our piecewise function. Oh, okay. Well, let's see. So, and we get nicely, the pieces are different colors. So you can see as we approach 1 from the left, the y values get closer and closer and closer and closer to 3. They don't actually get to 3, right? Because if you actually, right, you can't actually plug in 1 for that first piece, because technically the way the function is defined is that when x is 1, the y value is going to be 6. Because this middle piece is the piece where x is actually equal to 1. But I will point out that the limit as x approaches 1 from the left is still positive 3, because the y values get closer and closer. Right, the y values get closer and closer and closer to 3 as the x values get closer and closer and closer to 1. Right, we don't actually get the value of 3, but we're not asking what value we actually get. We're asking what value we get close to. And I'm going to keep emphasizing that distinction because it's a really important one. Right, the limit is only concerned with what actual number are the y values getting close to. You might not actually get there, but you're getting you're getting literally as close as humanly possible. Right, there's no distance between the number you're actually going to, because you might say, well, James, you can get to 2.99. Someone else will be like 2.99999, and you can keep going forever. And if you said 2.9 forever, well, then we'd have to have a discussion about how that's actually equal to 3. Because it is. I know it might sound weird, but it is literally true that I'm going to use this example instead. We'll talk about this another time, but it is literally true that 0.9 repeating is equal to 1. Not like approximately, not like that. I don't even know how to say something else. They're actually the same number. Just like 1 is also equal to 6 over 6. It's just another way of expressing the same thing. It's a little strange to think of this 0.9 forever. You might say, well, Dave, there's something between 0.9 forever and 1. I would be like, no, there isn't. You can't find a number that's between 0.9 forever and 1. And if there isn't a number between two numbers, they are the same number. I know we're getting a little esoteric here, but it's true. That is a feature of the real numbers. If there isn't a number between two numbers, they're the same number. Or more conveniently expressed, any two numbers that are different, there is at least one number between them. There's actually an infinite number of numbers between them, but we won't go. So, lastly, for this example, maybe the least interesting part. Sorry, I lost the chat. Is the limit as x approaches 10. So I want to find the limit as x approaches 10. Well, 10 is kind of a non-issue because when we're looking at 10, well, when x is 10, we're totally in this area, whether we're on the left of 10 or on the right of 10. So when you want to find the limit as x approaches 10, we're just saying, well, that's the function x minus 1. And whether you're approaching it from the left or from the right, x minus 1 is still getting closer and closer to the same value, which is 9. Right, we can also look at the graph on Desmos again if you want. Zoom out a tiny bit. So you go over here to 10, right? You can kind of see, oh yeah, whether you're on the left of 10 or the right of 10, the y values are getting closer and closer to 9. And again, in practice, you're not really thinking that hard about it. You're just saying, oh, I know when x is bigger than 8, the function is defined to be x minus 1. So as x approaches 10, we literally just, what we say is we plug in 10 for x and get 10 minus 1 from that. And this is an example of what's called the substitution property for limits. Essentially, the idea being, sorry, you can't see what I'm looking for. Can't see what I'm pointing at. Essentially, the idea being that if you can plug in the value that x is approaching to your expression and get a number that works, you're good to go. It doesn't work for something like 8 because you have two different sides of what's happening there, right? On the right side of 8 and left side of 8, the function is different. But if your function is just one thing on either side of the number you're approaching, you're good to go. So another easy example would be to say, like, what's the limit as x approaches -3 of this function? Well, when x is approaching -3, you're clearly either on the left of -3 or the right of -3, you're using this piece. So you can say, oh, James, that's no problem. It's the limit as x approaches -3 of x cubed plus 2x. And then you just get to plug in -3 for x and get -3 cubed plus 2 times -3, which is -27 minus 6, which is -33. Sorry, you can't see that. If you can't see it and you need to see it, like this one, I feel like you can probably hear me say the words would be fine. But if you feel like you need to see a thing that you can't see because I'm off screen, just say something. And that goes for the Zoom people too. If you can't see something and you need to, write it in the chat or say words. And probably one of the students will see it and they'll let me know. And I'm not always looking at the chat. All right. So the real name of the game here for limits is, a lot of the time, or actually really all of the time, if you're trying to evaluate a limit, you should start by, can I just plug in the value that x is approaching and get a real number? And either you'll get a real number, you might have something piecewise like what we've just been looking at, where you have to look at both sides and then you have to do a little more work. Or you'll probably run into the situation where you have division by 0. And that's where you're going to have to do more work. So let's look at something like this. I want to find the limit as x approaches 9 of x squared minus 10x plus 9 over x minus 9. And I'll point out that if we plug in 9, we're going to have problems. Clearly, you can see you're going to get 0 in the bottom. It is also worth noting that you would also get 0 in the top. So when you look at limits, a lot of the time what's going to happen is you're going to get what's called a 0 over 0 type of limit. So, right, if I plug in 9, I get 9 squared minus 10 times 9 plus 9 over 9 minus 9. 81 minus 90 is negative 9 plus 9 is 0 over 0. And what I would say is 0 over 0 is what's called an indeterminate form. It's one of many. There's probably like at least 6 indeterminate forms we will cover at some point. Specifically, when we talk about L'Hopital's rule, we'll talk about more of them. But what indeterminate form means is it's just fancy words for it can be anything. And you'll have to remind me, I think we talked about this a little bit last time. I said, what's 0 divided by 0? And I was like, well, it's 7, or it's 5, or it's a billion, right? Because 0 goes into 0 as many times as you want it to, or as few times as you want it to. But the point of that was, it can actually be anything. So we have to figure out what it is in this particular example. So here's how we typically do it. Usually when you have what's called a 0 over 0 form, you're going to do some sort of simplification before you try to evaluate it. So how do I want to say this? So this is where I need to go back and re-emphasize what I said before. The limit does not actually care what's happening at x equals 9. The limit really cares about what's happening as x gets closer and closer and closer and closer to 9 from either side. But in this case, it's the same function on either side. So here's what we're going to say. This is equal to, I'm going to do some factoring. And typically when you have a 0 over 0 form, you're usually going to simplify it by doing some sort of algebraic manipulation. In this case, the numerator factors is x minus 9 times x plus 1. Sorry, x minus 1. Oof, come on, James. Divided by x minus 9. Now, I'm going to do something and then we'll talk about it. These x minus 9s cancel. So this is equal to the limit as x approaches 9 of x minus 1. And then we can use the direct substitution property, which says just plug it in. And we're going to get 9 minus 1, which is 8. Here's what I want to say. This function here is not actually equal to x minus 1. It is most of the time. Well, let me show you the difference. We'll come back to that. Don't worry. So x minus 1. Yeah. So here's y equals x minus 1. And here's the other function. I'm going to zoom out for a minute. I want to be able to show you both things at once. And this, if I plug in, 9. And here's the other function. Here's f of x equal to x squared minus 10x plus 9 divided by x minus 9. It's literally the same function minus 1 point. This function doesn't have the point 9, 8. It is undefined there. But everywhere else, when x isn't equal to 9, that function is equal to x minus 1. In fact, people typically rewrite this function as f of x equals x minus 1, except x can't be 9. And now here's why we get to do what we just did. Because the limit doesn't care what's happening at 9. Right? As far as the limit's concerned, this function and this function do the same thing as x approaches 9. They both get close to the same y value. We don't care that this one is undefined at 9. We only care that as the x values get closer and closer and closer and closer and closer to 9 from either side, the y values get closer and closer and closer and closer to 8. Same deal here. As the y values get closer to 9, the x values get closer. Sorry, I said the wrong thing. As the x values get closer to 9, the y values get closer to 8. So why am I making a big deal about this? Well, because that's how we're justifying our ability to do this algebra. That's why it's okay to say that the limit of this expression is equal to the limit of this expression. Because the only thing we're canceling out is the part where it doesn't matter if they're different, right? It doesn't matter that we're canceling out the part where 9 makes it undefined, because we don't care what happens at 9. And that's typically what's going to happen for almost all these things. Like if you have a limit as x approaches 3, you're probably going to end up canceling out some sort of x minus 3 over x minus 3, or something like that. That's kind of the whole idea, is that when you have a 0 over 0 type of limit, you're trying to essentially disappear a factor that's giving you the 0 in the numerator and the denominator. That's what we've done here. We've gotten rid of the piece that makes the top 0 and bottom 0. And then we can deal with the rest fine, because we know that this function and this function act the same everywhere that matters, everywhere that isn't 9. And everywhere that isn't 9, but close to 9, these functions are both getting close to a y value. So I know that's kind of a lot of explanation for something that's actually fairly simple in practice, right? The algebra is not hard here. We can do the factoring, we can do the canceling, we go, okay, we factored, we canceled, we plugged in x equals 9 for the remaining x and got 9 minus 1. But I do want you to really think about the idea, right? It is a worthwhile thought process to go through this. Oh yeah, the reason we're permitted to do this is because when we talk about the limit here, we're really concerned with not what's actually happening at 9, what's happening close to 9. Close to 9, this thing and this thing are exactly the same. At 9, they're not. At 9, they're totally different. This one is very undefined, and this one is very defined. But close to 9, they do the same thing. So then it's easy to be like, oh, well, I know what this one does when we're getting close to 9. It's easy to evaluate, which means this one has to be the same. But in practice, it's an algebraic process, right? When you actually do these problems, you're not going to really be thinking about, oh, yeah, what's happening? This is the same as this, even with canceling. You just be like, I'm going to do some algebra, I'm going to plug some stuff in. So let's look at another example where we will do less thinking and more mathing. Which I know sounds kind of backwards, but it's all right. So I can't make that. Let's just. So let's try and evaluate the limit as x approaches 2 of 4x squared minus 3x minus 10 divided by 6x squared minus 12x. And it's always a good idea, and I have to forget this, you should remind me. It's always a good idea to substitute in x equal to whatever it's approaching in the very first step. Because sometimes you're just going to get a number. Most of the time, you're going to get 0 divided by 0. But sometimes you'll get like 0 divided by 5, which is equal to 0. Or you might get 3 divided by 4, which is your answer, 3/4. You're done. But if we plug in 2 here, let's see. 4 times 4 is 16, minus 6 minus 9. Okay, that's 0. And the bottom is 6 times 4, which is 24. Yeah, that's also 0. So it is a 0 over 0 thing. Okay, so we want to factor as much as possible. And the numerator looks like a little challenging to factor. Let's start with the denominator. So what can I factor out from the denominator? And what am I left with? And there's a really good observation to make here. x minus 2 is the factor that's making things equal to 0. And we know that if the top is also 0, when you plug in x equal to 2, which we literally just did, x minus 2 should also be a factor of the top. It's actually what's called the fundamental theorem of algebra. That if x equal to 2 or x equal to a number makes an expression equal to 0, the x minus that number is a factor of your polynomial. So I don't know exactly how this factors off the top of my head, but here's what I do know. I know that x minus 2 needs to be a factor. And then I can make the rest work. I know that I need another piece because it's quadratic. And I know x times something has to equal 4x squared. Well, great, I need a 4x there. And negative 2 times something has to equal negative 10. I need a positive 5 there. I'm 100% sure that's right, even without checking my work. Let's check just to make sure that. You multiply it out, you get 4x squared, you get the minus 10. And then the middle part is 5x minus 8x, which is giving you the negative 3x. But I want to make it really obvious to you all. If you have factored, like if you see that x being 2 is going to give you 0, you know that x minus 2 needs to be a factor if it's a polynomial. So I really didn't know how to factor it. Like I could have done some work. Like if I didn't know that x equaling 2 was a problem, factoring this would have been a lot harder because I would have been like, okay, well, it could be a 2x and a 2x or a 4x and an x. But knowing that 2 makes it 0 gives me some inside information. So don't work harder than you have to, right? Knowing that x minus 2 is a factor here makes it really easy to find the other factor because these need to multiply to that and these need to multiply to that. And then cancel those out. Get the limit. What time is it? Oh, it's time to end. The limit is x approaches 2 of 4x plus 5 over 6x. And then you just jam a 2 in there. And you get 4 times 2 plus 5 over 6 times 2, which is 13 over 12. And that's your limit.